Hello and welcome to another video lecture. Hope you're all doing well. All right, so today we're going to talk about parameter estimation. And we've talked a lot about population models and we've talked a lot about parameters. We've talked a lot about R max and per capita birth rate and per capita death rate. But we have really not spent very much time talking about where these parameters come from. All right, so that's what we're going to talk about today. This is a major focus of NRES 488, which is the next class in this wildlife ecology and conservation sequence. But I think it's such an important topic, and it's kind of a fun topic, that we'd be remiss not to cover it a little bit in this class. So that's the focus of this lecture. Now, you've already done some parameter estimation as part of your final PVA projects, and you've probably struggled a little bit with it. You've probably found some cases where you couldn't quite get exactly what you wanted to get out of the literature. And so it's definitely a topic that's probably been on your minds a little bit. And we'll talk about it more. We'll talk about all those cases, like where do the parameter estimates come from, that many of you are getting from the literature, and then what do we do when we can't find exactly what we're looking for? How do population modelers actually do it? So let's start with the data requirements. Let's start with let's just start even simpler and talk about what parameters we need to estimate for some of these models. We'll start simple, and this is just kind of a review. We've already gone over a lot of these parameters, but let's start simple and get more complex, just as we have in the whole class. So let's start with the simple scalar models. Those are the kind of models we started talking about at the very beginning of the class, where we didn't have age structure. We just considered n being the total abundance in the population. We don't dig in any further and divide n into juveniles and adults or anything like that. N is n is n. So what do we need for those types of models? What parameters? Well, of course, we need initial abundance, n0, n sub 0. We need to know R, or R max, right? That's the intrinsic rate of growth. R for the exponential growth model, and R max for like a density-dependent logistic growth model. We need to know the variation in growth rate. So thinking about stochasticity, what can't we predict about the future, and how variable is the per capita growth rate, for instance, and how can we simulate that using a random number generator? What's the carrying capacity for a ceiling density dependent model or a logistic growth model? We need to know the carrying capacity, so that's another parameter we need to know. If we start thinking about age-structured or stage-structured models, we need to know the initial abundance, not just of the total population, but the initial abundance of every stage that we want to model. So we need to know the total number of hatchlings, the total number of juveniles, subadults, whatever, right? And we also need to know the vital rates for each of those stages. When I say the vital rates for each of those stages, basically what I mean is each element in the transition matrix. Those are kind of the vital rates for a stage-structured model. We need to know what percentage of juveniles stay juvenile. We need to know what percentage of juveniles transition to adult in the next stage. We need to know the fecundity of subadults. We need to know the fecundity of adults. So there's lots of pieces of data that we need. Or there's lots of parameters that we need to estimate, basically, for these types of models. In addition, if we start thinking about stochasticity, we need to know the temporal variability, the environmental stochasticity in each of those per capita vital rates, right? So for every single one of those, they could be variable based on the quality of the habitat or based on the environmental conditions that year or the next year. So that's a lot. So we need to be able to potentially develop a random number generator for each of those per capita vital rates, each of the elements of the matrix, which is kind of a crazy thought. That's a lot to do. And there are ways to simplify that. So we don't necessarily have to develop a mean and standard deviation for each one of those. Sometimes one vital rate or one transition rate in the matrix is much more variable than the others, much more sensitive to environmental conditions. So we might only model that one. Say it's juvenile survival or fecundity that is much more affected by environmental conditions than others. So maybe we can make a simplification that the others don't really require a random number generator for environmental stochasticity, just that one transition rate. So we can simplify. And then finally, we have to start thinking about density dependence. Which of those vital rates, which of those transition rates in the matrix are most sensitive to density of the population, and how? Is it linear? Obviously, we have to make some simplifications sometimes, but it's an important thing to think about. And many of you are struggling with that right now with your own PVA models. How to implement density dependence? What's realistic? All right. And, if we start getting into spatial models or metapopulation models, we have more parameters to estimate. We need to know the spatial distribution of habitat patches. We need to define those patches. We need to think about potential variation in the vital rates. Like, how does habitat quality or differences in habitat quality among the patches affect the vital rates? Which vital rates are affected? When you have a higher quality patch, do you have more fecundity? Is that what happens? So we need to define how habitat suitability differences in patches affects our vital rates in order to build a realistic metapopulation model. We need to know correlation in environmental stochasticity. If patches are really close together, is a good year in one patch also going to be a good year in another patch? Or are they not correlated? So that can be really important in modeling metapopulations in a spatially explicit way. And we need to know dispersal rates among patches, of course. We need to know what percentage of individuals from one patch disperse to all of its neighboring patches. And we need to know, perhaps some patches are better quality for some life stages. Perhaps different life stages require different types of habitat. And that is pretty common as well. So we might have to get even more complicated and think about the spatial and habitat requirements of juveniles versus adults. And finally, we might, if we're building a classical metapopulation model, we're going to need to know the rates of extinction in each patch. We need to know the rate of colonization. So if we're dealing with a classical metapopulation, those are the kind of parameters that we're going to try to estimate. All right, so those are the parameters. That's just kind of a review of what we've already gone over. Now, how do we estimate them? That's the real topic of today's lecture, parameter estimation. So we're going to go through a few sources of data. Some of you have probably seen these sources in the literature as you try to parameterize your final PVA models. We're going to talk about life tables. We've talked about life tables before, but life tables are a common way to get parameters from the literature. And so we'll mention them again here. And I'll talk about what's called census data. I'll talk about mark and recapture data. All right. And then I'll talk about the case of no data, which many of you are dealing with in your final projects. So let's go back to the data sources, life tables. As you recall from earlier lectures, a classical life table represents a single cohort that's been followed over time until the last one has died. So you might take a cohort that starts off with 500 individuals that are just born, right? And then follow them over time. And at year 1, there's 400 left, 100 have died. At year 2, 200 left. You also keep track of the number of individuals that are born per female in the population, and that would be the B sub X, assuming these are all females. And this is per capita birth rate, and this is survivorship, and this is survival rate. All right. So we oftentimes might see a life table from the literature. There's a lot of published life tables out there for a lot of different species, and that can be a way for us to get what we need for our population model. And so some of you probably encountered that. Now, there's a very important note here. When you see a life table that's published for a wild population, it's nearly impossible to follow a single cohort over time in the wild. So when you see a life table, it's actually not generally derived by following a single cohort through time. That's how we think about a life table, but it's not how the life table was constructed originally, as if it's for a wild population, all right? So in practice, most published life tables for wild populations are called static life tables, in which we basically look at the different age classes or stage classes for this population at a single point in time. So it's called a static life table, and we're looking at the population size of 1-year-olds, 2-year-olds. If we can age individuals in the population, we're going to look at a single point in time and try to construct a life table just based on the data from that one point in time. How many newborns are there right now? How many 1-year-olds are there right now? How many adults are there right now? All right. Then we can if we assume that population's in a stable age structure, at stable age distribution, that means that distribution of newborns to adults to juveniles, whatever, that distribution should be constant over time. If the population's at stable age distribution, as you know from your earlier models with age structure, if the population's at stable age distribution, that distribution does not change over time, right? So if we assume stable age distribution, we can then kind of reconstruct what the survival rate should be, and so on and so forth. And we can basically construct a life table that way and get a survivorship and fecundity schedule for the population, which is great, but it's kind of fraught because the problem is this assumption that a population's at stable age distribution, that's often violated in natural populations. It's not true almost universally for almost any population. They're not in stable age distribution at any given time due to environmental stochasticity, whatever. The stable age distribution is not necessarily a common thing to see in nature. So it's not a great assumption. But in the absence of better data, maybe this is better than nothing. So be careful about life tables because they often represent a single snapshot in time that may not be generally relevant. All right. So the pros of using life tables to parameterize your population model to get survival and fecundity estimates, well, it's often available in the literature. So it is a good source because that's oftentimes all we have and that's what's available. But be careful when using data from life tables because those static life tables are not very trustable. They make unrealistic assumptions. And also be careful because some life tables come from captive populations. Captive populations might not represent wild populations very well. So be careful about that as well. So the cons, again, of life tables, unrealistic assumptions. We can't really estimate environmental stochasticity because it just represents one snapshot in time. We oftentimes don't have any information to go on to estimate environmental stochasticity from that. And we can't estimate density dependence because, again, one snapshot in time, unless we have multiple life tables that represent the population at different densities, we can't really estimate density dependence from a single life table. And we ignore the possibility that, we can't see all the individuals. We can't detect all the individuals. For wild populations, almost inevitably, we can't detect all the individuals in the population. They're difficult to detect. That's by design because due to predation pressures, individuals of most species do not want to be seen. And so they make themselves invisible to us in many cases. They go underground. They use cryptic coloration. For whatever reason, we can't detect them all. So making an assumption that all individuals are detectable is often an unrealistic assumption for wild populations. And you also can remember that some, like juveniles, can be harder to detect than adults in many cases. And so if you just count up the number of juveniles or the ratio of juveniles to adults that you see, that might severely underestimate what's in the population in reality, because you miss a lot more juveniles than you miss adults. So for a lot of reasons, this isn't perfect, but sometimes it's the best we have. What about census data? What is census data? Well, census data is what we wish we had. It's for all populations. It's when we have perfect detection, which I already said is unrealistic for most populations. But if we have perfect detection, then we can go out year after year and count up the total number of newborns, the total number of 1-year-olds, 2-year-olds, 3-year-olds in the population at any given time. And so here's an example where we went out in 1995, 1996, all the way through 1999, and we counted up all the newborns, all the 1-year-olds, all the 2-year-olds, all the 3-year-olds. So not only do we have perfect detection here, we can age the individuals perfectly. So disregard the fact that this is completely unrealistic. This is exactly what we wish we had, because we can estimate just about everything we would want to estimate, all the parameters we want to estimate for a population from census data. All right. So let's just look at this for a second. How can we estimate, for example, the survival through the first year of life? Just think about that for a second. So look, when we start off in 1995, we go out in the field and we count exactly 289 newborns. How many are left in 1996? If you look at that and see that 119 1-year-olds are in the population at 1996, those 1-year-olds have to be those same 289 newborns that were there the year before, right? So all we have to do is divide and say 119 divided by 289, that is equal to 0.412, right? So we take 119 divided by 289. That's the survival rate of newborns in 1995. What's the survival of newborns in 1996? Well, we take 143 survivors in 1997, divide by the total number of newborns that were born in 1996, all right? And that was 363. And so we can get this newborn survival rate for this year, this year, this year, and this year. So we have 4 estimates of newborn survival rate, right? We have 0.412, 0.394, 0.439, and 0.313. That is great, because not only can we compute the average survival, which is 0.38939, that's a lot of significant digits. I wouldn't recommend using that number, but what can you also do here? If you think about stochasticity, you could also estimate the standard deviation in newborn survival. So you can get this, not only can you get newborn survival, but you can get the standard deviation or environmental stochasticity in newborn survival and the per capita survival rate. So that is cool, right? Can you also do that for the survival for 1-year-olds? Yeah. 2-year-olds? Yeah. 3-year-olds? So you can do that for every age class in this population. We can get the average survival, and we can get the environmental stochasticity on those survival rates. So that's great. Census data is pretty cool. Well, what if you have a stage class instead of an age class? So everything that's 7 years old or greater is classified as an adult, all right? So in that case, maybe what we'd want to do is say, okay, how many adults were there in 1995? Well, we take the 7-year-olds and the 8-year-olds together. That's 21 adults. And how many survivors do you have the next year? Well, you have 14. And so you just say 14 divided by 21 in that case, and that gives you an estimate of adult survival rate. All right. So that's when you want to pool together multiple ages into a stage. And what about fecundity? We can also estimate fecundity easily using census data. So Let's imagine that everything that's 2-year-old or greater can produce offspring. All right? And remember, fecundity represents the number of offspring produced in the following year, right? So you have to survive and produce offspring. And so in this case, we have this number of reproductive adults, right? 67 plus 33 plus 22. And we have this number of newborns produced the next year, right? So you just take the number of newborns produced the next year, divide it by the total number of reproductive or potentially reproductive adults this year, and you can get fecundity really easily. Not only can you get fecundity for 1995, which is what we calculate here, 363 offspring produced next year by all these individuals in 1995, but you can do it for 1996, 1997, 1998. So we can get, again, a mean fecundity, and we can get a standard deviation on fecundity from these data. So this is relatively straightforward. You take the number of possible reproductive adults, you take the total number of newborns produced by them in the following year, and just get a fecundity. In this case, what we calculate here is a fecundity of 2.161 for 1995. All right, we can do the same for the other years, get a mean and get a standard deviation. And we're really good because we have all the parameters we need in that case. All right. So the pros of census data. Well, yeah, we can do a lot with it. We can estimate survival, fecundity, environmental stochasticity, density dependence. I didn't mention density dependence, but we can compute density dependence from that because we know the total abundance, right? We know the total abundance in each year, and we know the vital rates in each year, and we can look for a relationship between survival or fecundity and density just using this data. This is all the data we need to estimate all sorts of parameters, pretty much everything we would want for a population model. What's the con? Well, it's never available to us. We don't have this information. It is pretty much impossible to get census data for a wild population. We can do it for captive populations, but that's not that useful because captive populations don't really represent wild populations very well. So that's the problem with census data. It's what we want, but it's not what we have. So that leads us to the next source of data for parameter estimation, and that is called capture, mark, recapture data. And this is what the optional Lab 7 is all about, and a lot of NRES 488 is devoted to analyzing capture, mark, recapture data. Why is this topic so important for wildlife ecology? Well, it's realistic. We can compete. We can get this kind of data. All we have to do is go out into the field and mark individuals. We capture as many individuals as we can. We acknowledge that we can't capture, we can't observe all the individuals, but when we do capture an individual, we can give it a unique mark. We can do this in any number of ways for many different species. Some species, ear tags work well. For some species, like turtles, what we can do is put little notches. We can file notches into their shell. For some species, what we use are called pit tags, passive integrated transponders that we can basically insert under the skin or in the abdominal cavity or somewhere where it's not going to get dislodged and it's going to stay for the whole lifetime of the individual. And you can just wave a wand essentially over the animal and it will detect exactly what individual it is and give the unique code that represents that individual. And so every time you capture that individual in the future, you'll know exactly who it is because you can wave the wand over it and the receiver will tell you what individual that was. All right? And so it's not difficult to do. It's a straightforward way to monitor a wild population. You just have to capture individuals that you can capture, mark those that are not marked, and record the marking for those that are marked every time you go out. All right? That's all you have to do, and this is a very common way to monitor wild populations. And the best part about it is that you can estimate survival, variability in survival or environmental stochasticity. You can estimate lambda. You can estimate recruitment. You can estimate dispersal. You can basically estimate everything that we need to estimate from wild populations using capture, mark, recapture data. And there are few downsides to it. It acknowledges the fact that it's unrealistic to think that there's perfect detection. We're able to relax the assumption of perfect detection. We can use these data to estimate the detection probability and therefore correct for it. So we can get unbiased estimates of survival and fecundity and recruitment. There's very few downsides. The only problem is it takes a while to master the analytical techniques involved in, processing and using these data. So it takes a little while. It's a bit of a learning curve getting familiar with this, and we'll go through a little demo example at the end of this lecture. And if you want to get hands-on experience using these data, please, I encourage you to go to Lab 7 and complete the exercises. You get some extra credit for it, and I think it's really useful exercise to go through, and it'll get you really well prepared for taking NRES 488. All right. But before we go on and talk about capture, mark, recapture data in more detail, I just want to talk a little bit about what to do if there is no data. All right. So, all right. So remember the stone soup analogy? That is, even when you think there's nothing, there's no food, nobody has any food, nobody has any data, there's probably more than initially appears. You can kind of like use creativity and put things together and try to understand, at least you get some information about some of these parameters that you think you have no information. You actually do have some information when you really, really think about it. And there's some techniques for doing this. So one way we can kind of get something from nothing is we can use algebra, use basic algebra, basically solve for x sometimes. So imagine we don't have any information on hatchling survival. It's complete lack of information because hatchlings are, for whatever reason in this species, and this is actually true for some turtle species, you basically can't find them. They're buried. They're almost impossible to find. So we can't really estimate survival if we can't ever mark them. Even in a capture, mark, recapture, you have to be able to capture them in order to be able to estimate survival. So what do? Well, let's imagine we do know juvenile and adult survival rates because we're able to capture those individuals and we're able to mark them and get estimates from capture, mark, recapture. We have nesting success data, so we kind of know something about their ability to nest. We just don't know the survival of those hatchlings for that first year of life. That's the only thing we don't know. We also know the population growth because we've monitored this population for years, and we know that the population is growing at approximately a lambda of 1.09. So we have all this information, and because we know that lambda is 1.09 and we know all the vital rates except for hatchling survival, we can basically say there's only one hatchling survival rate that could cause a lambda of 1.09. So all we have to do is kind of vary that hatchling survival until we get a lambda from our matrix of 1.09, and that is that's the hatchling survival rate that's most realistic because it's consistent with our observation that lambda is 1.09. So basically we've solved for x. We now have a hatchling survival rate because we matched the lambda from our matrix with the lambda that's been observed. And you can see an example of this if you click on the link. This paper here is actually a paper that I've cited many times in my work. I think it's a very important paper if you like to model turtle populations anyway. And they used this technique because they did not have a survival rate for the really young turtles, but they kind of solved for X and they got a survival rate for the young individuals. I think they got this 0.7826 by solving for x. They knew the lambda, they knew the survival rate of adults, but they did not know. I think I actually got that wrong. I think it's the 0.2610 that they didn't have. They did have the survival rate for juveniles. They did not have the hatchling survival rate. And so that 0.2610 is actually achieved by solving for x. And they knew they had a approximately stable growth population of lambda of approximately 1. And so they were able to get that estimate there. All right. Let's go back to the lecture. Another thing we can do if we don't have enough data, we can simplify. Maybe we tried to make a really complex model, but we just don't have enough data to parameterize that complex model, so we make a simpler model. Maybe we know that age structure could be important, but we don't have enough data to build an age-structured model, so we use a scalar model where we just model the total abundance and the intrinsic rate of growth, and the variability in that intrinsic rate of growth. Maybe that's all we can do for our model. Sometimes we don't have any information on density dependence, and I'll talk about that in the next little section here on the conservative strategies that we could use, or the worst case scenarios. But we might want to just ignore density dependence. Perhaps our question's not really focused on density dependence anyway. So we can just simplify in various ways. We might ignore trophic interactions. Maybe, we know that, predators can cause a big impact on population growth for your species, but you really don't have any data to explain how predators affect the vital rates. And so you might simplify by just, ignoring trophic interactions. And as long as your question allows you to simplify it in this way. Remember, all models are wrong, but some are useful. So just keep that in mind. You're always trying to find a balance between complexity and simplicity and being able to answer your question. So this is this whole goal here of simplification is just trying to find that balance, and sometimes the balance is closer. You have to simplify more because you just don't have the data to do anything more. And sometimes maybe we can ignore abundance entirely and just use a classical metapopulation model. We don't have any good information on population dynamics, but we do have information on whether sites are occupied or unoccupied. So let's build a classical metapopulation model. Let's not even do a population model with abundance or age structure or density dependence, right? Sometimes we just want to use a conservative strategy. A conservative strategy often means just take the worst case scenario, because sometimes we're just interested in knowing the extinction risk for a population, and we don't really know the parameter estimates fully, but we do have some lower limits of like the worst case scenario. And maybe we want to present those because we want to know, well, in the worst case, what's our extinction risk, right? And maybe the worst case scenario is still okay. Maybe it still falls within a reasonable bounds where we're able to be satisfied that the population's not at severe risk of extinction. So, and if it's not at severe risk of extinction in the worst case scenario, then clearly it's not at risk of extinction in better case scenarios. So this can be a good strategy when we don't have enough data. For example, a density independent model is often conservative. That is, if you do not include density dependence in your model, it's often conservative. And why is that? Well, in a density dependent model, as the population gets smaller and smaller, the vital rates get more and more favorable, at least if you're talking about a negative density, like logistic growth type model. As the population gets smaller, the vital rates get more and more favorable, and it becomes less and less at risk of extinction. But if there's no density dependence, as the population gets smaller, there's no rebound in the vital rates. The population vital rates don't improve, and that means that the population might be at higher risk of extinction because there's no process compensating for the smaller population size, right? And so sometimes we can ignore density dependence and we'll just say in our method sections as we're writing this up, we didn't have much information on density dependence, but we chose to use a density independent model that assumes that the vital rates that have been estimated for this population at a higher density will hold even at lower densities. And that's conservative because in many populations the vital rates will actually improve at lower densities, but we did not have the data to actually say that. So we declined to actually put that in our model. That's often a good strategy, especially when dealing with conservation questions. We can sometimes use data from similar species. I think some of you have done this with your final projects. For example, we might be trying to model golden-headed lion tamarins, but we only have data on golden lion tamarins. Well, it's not a crime to use that data. It's the best we have, right? And expert opinion. Sometimes all we have are some experts who've worked with the species and have some hunches about what the survival and fecundity rates might be, or what the population size might be, or what the trend in population size or lambda might be. So it's not a crime to use that, but there are some caveats, and I'll go over those in a second. We sometimes can get data from national databases that we might not realize exist. That's more useful for things like habitat suitability and that kind of thing for modeling. There's a lot of spatial data that's out there that might be able to help you define how much habitat there is, which might help you define what carrying capacity is. Even if you think you don't know anything about carrying capacity, maybe you'll be able to get it using one of these methods by taking some existing spatial data layers and manipulating them and finding something that is better than nothing. And finally, if you have nothing and you still have nothing after going through all these different types of options, well, you have allometries. And this is sometimes called macroecology, where you just take variation across all life forms essentially on Earth and you try to develop patterns or try to see patterns in this data, right? Data for all sorts of species, from bacteria all the way through elephants, basically. And you can find patterns. So you can say, okay, there's relationships between body mass here on this log scale here, and between that and your intrinsic rate of growth. This is a per day rate of growth. If you're really small in body mass, like 1 femtogram, maybe you're a virus, I don't know what you are here, but you can grow at a rate of 500 times per day. You can multiply by 500 times per day. Whereas down here, maybe you are a blue whale or something like that, one of the largest organisms on Earth, and your rate of growth per day is more like 0.0005. And so you can see that there's a relationship. Obviously, elephants can't multiply like bacteria. And you might be able to use this kind of relationship. So you know that your organism is exactly, let's say, 3 milligrams. Now we know that your R max, your intrinsic rate of growth, should be 0.1, So you can get some kind of information from these types of what are called allometries, all right? And you can read more about allometries if you'd like. I think I put a link somewhere. There you go. So if you want to read more, this is an article called Does Ecology Have Laws? It's kind of interesting article and talks about all these different types of allometries, and you can see the brilliant people who came up with some of these allometric relationships. All right. And before we move on to capture, mark, recapture analysis, just a brief aside, is it okay to use expert opinion? And this is kind of a big debate in the conservation modeling world, because sometimes really expert opinion is all we have. So sometimes the way we build these models is to convene large groups of experts who've worked with the species or have an interest in the species and build a model together by kind of like coming up to a consensus about what the vital rates are. We basically parameterize the model just from experts. And, this is not perfect because we'd ideally like empirical data rather than opinions about these parameters. But sometimes it's all we have, and it's better than nothing. It brings a community of stakeholders together. It allows us to figure out what we do know, what we don't know, and it allows us to understand how our lack of knowledge might affect, might have implications for, what we think about the future conservation outlook for the species. So we get a lot out of this type of, developing models by opinion, by convening experts. So it's definitely better than nothing, but it's not perfect. So it's not ideal. It's hard, impossible to validate the parameter estimates we're getting. We don't have data. Without data, you can't validate anything. But it's oftentimes, what we'll do, what we have to do in some cases where there's very little information. It's better than nothing. We just have to document the process that was used to elicit expert opinion, and that is how this model was built. And it is a starting point, and hopefully it'll go on to prompt more data collection, and future models will be more validated, more based on data. All right. I'm going to stop here for now. In the next video, we're going to talk about capture, mark, recapture analysis.